So our next presentation will be from Frank Schulnies, and he will tell us a little bit more about caking of dairy powders. A little bit background about Frank. Frank studied food technology at master's level at Anhalt University in Köthen. Since 2010, he is working as a research associate in the working group of Professor Dr. Thomas Kleinschmidt. In the past, he was working on different AIF or FEI research projects as a project leader. And his main research interest topics are spray drying, encapsulation, powder characterization, powder flowability and caking, and powder solubility. So over to you, Frank.
Yeah, thank you, Daniel, for your introduction. So yeah, my topic today is caking of dairy powders. I want to speak about this topic, and let me give you at first a short overview over my presentation. Yeah, at first I want to define caking and speak about the consequences. After this, I want to show some caking mechanisms which are relevant for dairy powders and also other powders, of course. Then let me give you a short introduction to dairy powders. And then after this, I want to present some of our research results about the caking behavior of dairy powders. And at last, I want to give you a short summary. Yeah, definition and consequences of caking. What is caking actually? Caking can be regarded as a time consolidation process during storage. And yeah, during storage, the interparticle adhesive forces increase with time and the flowability decreases. And yeah, here you can see some pictures we took in our laboratory. The result of these caking is the formation of lumps, or even a massive block can form. Yeah, from experience, we know that about 60% of powders and bulk solids exhibit caking problems. Yeah, and of course, a powder should not look like this. The customer will not be very happy with this kind of powder structure. Here are some consequences shown. What is the result of caking? Of course, the quality is lowered, the functionality is lost, maybe also. We have process interruptions, process schedules can be missed. Also, we have maybe a drop in production rate due to blockage of pipes or breakage of fluidized beds at high air humidities. And also we need decaking manufacturer when we have a cake product, and this costs extra time and equipment and manpower. You can see here when an arch is formed in a funnel, then yeah, you need something to get the powder flow again. And the assumed costs related to caking problems are assumed to be 0.5% of all finished powders. But however, it's quite difficult to get reliable data because these problems are often handled internally. Yeah, here are some caking mechanisms which are relevant for food powders. On the left side here, you can see the humidity caking. Humidity caking is yeah, facilitated by liquid bridge formation at low water activities. Water molecules adsorb at the powder surface, but when the relative humidity exceeds 60% or 60 to 85, then there's a possibility for capillary condensation. And this liquid bridge will increase then the adhesive forces between the particles. The material can then dissolve into the liquid bridge, and when then the relative humidity is decreased again, then of course the liquid bridge solidify, and yeah, when it's a crystalline material, recrystallization can take place, and a crystal bridge can form, and this will increase then the adhesive forces also. The second mechanism is the mechanical caking. Mechanical caking can be defined as a powder consolidation due to mechanical pressure, and within this process, particles approach each other, and then the contact area is increased, which will also increase the van der Waals forces. The distance is then lower between the particles. And yeah, also interlocking can happen during transportation or vibrations. Here, particle shape is an influencing factor. You can imagine when you have needles or plate-like particles, then there's a possibility for interlocking to take place, which can form then also a cake. The amorphous caking is relevant for materials which have this amorphous state and the glassy state. In an amorphous caking, the material changes from a glassy to a rubbery state in the glass transition range. There is a decrease in the viscosity, and thus the material can flow to the contact points. So, and then sintering occurs. And this sintering is governed by the temperature difference between the storage temperature and the glass transition temperature of the material. This governs then the caking rate. Here you can see in the right side the picture we took under a microscope. Two particles here at the beginning of this sintering process, and after storage some time at high relative humidity, you can see that the material starts to flow here into each other, and a sinter bridge is formed. Yeah, the influencing parameters of caking I have listed here at the bottom. Of course, caking is influenced by the raw materials. These include composition, water activity. Yeah. Then the process parameters are important as an intrinsic factor. Here, the drying conditions and the concentrate properties play a role, as well as the packaging material. And as an extrinsic factors, the storage conditions are important for caking. Here, you can imagine that temperature, relative humidity, consolidation pressure, and also maybe vibrations are important for the caking process, which can influence this caking. Dairy powders. Dairy powders can be made of different raw materials. For example, whole milk. This is then the whole milk powder, or skim milk powder. They can also be made from buttermilk, whey, or protein concentrates. And yeah, milk powders have functional properties like emulsification, foaming, flavoring, and thickening. So they are used in a wide range of food products. They have various applications in infant formula, sports, and nutrition foods, bakery, or dry mixes. So a lot of usage of these powders. And yeah, the world production in 2020 was approximately 10.5 million of tons. And the most important powders are the whole milk powder and the skim milk powder. And yeah, dairy powders are usually, spray drying is the most frequently used technique for the production of spray dried powders. And yeah, in this technique, the fluid or the concentrate is atomized in a hot air stream, and the droplets are then dried by convective drying. And by this, particle sizes of 10 to 250 micrometer can be produced. The bulk density is in the range of 300 to 600 kilogram per cubic meter. And yeah, the residual moisture content is usually in the range of 3 to 6%, depending on the product specification and on the product type. And yeah, because of the fast removal of water during spray drying, the lactose is predominantly amorphous in this amorphous state. And yeah, this is a thermodynamic unstable material state where yeah, the probability for caking can be happened. Yeah, now I want to show you some material methods we use to measure caking of dairy powders. We investigated commercial skim milk powder and milk powders with different fat contents. We measured the unconfined yield strengths with a Schulze ring share tester and an uniaxial tester. Yeah, in uniaxial testing here, we can see our device. The powder is filled in a cylinder, and then the cylinder is loaded with weights, and when the storage time has elapsed, then these powder cylinders are loaded with an increasing normal load up to the point of failure, and the pressure needed to break the sample is then recorded, and this is then the unconfined yield strength. The share testing method is mentioned here at the bottom of the chart. In share testing, the powder is filled in a share cell, and then it's pre-shared until steady state flow is reached. And after this steady state flow, the sample is shared until failure under different normal stresses. And from these data, a yield locus can be established. And from these yield locus, the more stress circles can be derived. And the more stress circles then define the major consolidation stress and the unconfined yield strength. Yeah, and for time consolidation, of course, a yield locus has to be measured. And then after pre-sharing of the powder, the share cell is transferred to a consolidation stand. And it's stored for a period of time under a vertical acting normal stress, which is the same like the major consolidation stress from the yield locus. And so after the time has elapsed, then the powder is shared on the share cell, and one share point is measured. And this is done because usually time consolidation experiments are very time consuming. So the common practice is to measure only one share point after time consolidation. And then the time yield locus is approximated by a parallel to the original yield locus. And then, with this time yield locus, we can derive the unconfined yield strength after storage. We investigated regular skim milk powder in the glass transition range. The focus of the studies was mainly on this amorphous caking. We used the ring share tester for these studies. This is here the powder we tested. It had a particle size of 96 micron, moisture content of 4%, lactose 59%. So the normal, typical specification or the typical composition of a skim milk powder. We stored this powder at temperature levels of 42 to 50 degrees Celsius at a constant relative humidity of 22%. And we investigate different consolidation pressures during storage from C3 to 20 kilopascal. What else we did? We investigate the caking behavior of milk powders with different fat contents below the glass transition. For these studies, we used the uniaxial tester. And we investigate 3 different powders here: the cream powder, the whole milk powder spray dried, and a whole milk powder roller dried. They had different particle sizes here. And with these powders, we did a heating and cooling experiment. We heated up the powders to 40 degrees Celsius, and then we cooled the powders to 10 degrees Celsius. And at different temperatures, we measured the unconfined yield strengths. The relative humidity was kept constant in these experiments, and the consolidation pressure was 5 kilopascal. And now, let me show you some results of the caking behavior of skim milk powder. Here in this chart, the moisture absorption isotherm is shown, and also the glass transition function for the skim milk powder. We can see that that increasing water activity or relative humidity, the moisture content increases, and a quite small increase in the moisture content affects the glass transition drastically. You can see that the glass transition decreases here, and you can calculate the glass transition line with this equation here from Vuates. We use this to calculate the glass transition for different water activities. And yeah, the critical water activity for skim milk powder is a water activity of 0.35. Here, there the glass transition reaches room temperature, so we can expect then that at this temperature the rubbery state begins and the powder gets lumped. Yeah, all temperatures above this glass transition line, here is the material state, the rubbery state. The particles are sticky, so yeah, here caking can take place in this temperature range. Before we start with the results of the unconfined yield strengths, there's of course the question, when is the powder actually caked? So what cake strengths correspond to a cake powder? And for this, we did a sieving test. We consolidated the powder in the uniaxial tester. We produce cylindrical cakes, and these cakes were then sieved on a vibratory sieve shaker for 1 minute with an amplitude of 1 millimeter. And we measured also the unconfined yield strengths. And you can see here in this figure that with increasing unconfined yield strengths up to about 15 kilopascal, the compacts were fragile and completely destroyed by the sieving. But when the unconfined yield strength increased, then you can see that more and more powder was retained by the sieve. So then we suggest that a critical cake strength of 20 kilopascal, where powder begins to retain by the sieve, and thus we defined the caking time as time to reach this 20 kilopascal. These results were in good correlations with our qualitative observations during the share cell measurements. Here you can see some pictures after emptying the share cells. At the beginning, the powder structure was quite normal, and with increasing strengths, you can see lumps. These were fragile, but at 30 kilopascal, hard lumps were formed, and you need a lot of pressure with the spatula to destroy them. So this was quite a good correlation to this sieving test here. Yeah, here we can see the development of the unconfined yield strengths with storage time. We can see that the unconfined yield strengths increased nearly linearly with time for the different temperature tested. The caking rate is higher at higher storage temperatures and also increases with higher consolidation stresses. For example, at 50 degrees Celsius, you can see that the powder strength of 20 kilopascal was already reached within 4 hours. And at 42 degrees Celsius here, the caking rate was much slower, and the 20 kilopascal was reached after 40 days. So there's a big difference. And also with the lower consolidation stress, the caking rate was smaller. You can see the slope of the development is lower than at 20 kilopascal. The consolidation results from decrease in viscosity of the amorphous material. So the material stage changes from the glassy state to the rubbery state, and this allows the material to flow into the contact points, and a viscose bridge is then formed. This figure here shows the caking time as a function of the temperature difference between storage temperature and glass transition temperature for the different consolidation stresses we tested. You can see that a small increase in the temperature difference leads to a drastic decrease in the caking time. For 20 kilopascal, for example, here the caking time was approximately 130 hours at the glass transition temperature, and yeah, it decreased quite sharp here. And for yeah, let's say for 11 kilopascal, the caking time was much higher. It was about 450, about 600 hours here at the glass transition, and also decreases then with increasing temperature difference. Here on the right side, I want to highlight the influence of this consolidation pressure. A pellet, here's a pellet shown, the height of a pellet, and the corresponding caking times which induce caking in a certain height. So at the same temperature difference, the sacks in the lower part here are caked in a shorter time, you can see here, and with increasing storage time, then also more and more bags are lumped and caked. So yeah, this is then the problem with the storage pressure. And in this example here with the arrow, there is a pellet that needs, let's say, 3 days here to the customer. And you can see at an adequate storage temperature, you can see that only 30% or 30 centimeter of the bag of the pellet is caked. But when you increase then the storage temperature more and more, you can see more and more of the pellet is caked and lumped, and at 5 Kelvin above the glass transition temperature, nearly 70% of this pellet is caked. So a lot of product is then probably lost because of this pressure influence and storage above glass transition. We used also the results of the caking studies to simulate the caking tendency of SMP during transportation in a container. You can assume that although the water content at the beginning or at the after the production process is low, and the powder is far away from the glass transition, after some time it can happen that water permeates through the bag material and increases the moisture content of the powders. So what we did is we used real temperature and humidity profiles, which were recorded by a local dairy company in a container. This container was transported from Hamburg to Malaysia. And to estimate the cake strength, of course, we have to know the moisture content and the glass transition of the powder. And that's why we calculated the permeation of water vapor through the packaging material using the general transport equation, where the driving force is the water vapor pressure difference across the packaging material. And because we want to know the water vapor transfer rate here of the packaging material, we had to first estimate this by for this we placed dried zeolite in a cylinder, and we put this zeolite, we sealed it with the bag material and put it into a climate chamber, and we recorded the weight for 3 months to 6 months at 3 different temperatures to establish then the temperature dependency. So we were able then to calculate the permeability of this bag material with the Arrhenius relationship for every temperature. Here you can see some results of this simulation, the development of the cake strength. At first, of course, the moisture uptake in the bags, we simulated 3 different starting moisture contents from 3.8 to 4.2, and there is an increase in the moisture content because the water vapor permeates through the bag material, and from this data, from the moisture uptake, we could calculate then the glass transition line, which is important then for estimating the cake strength. We can see here that several times the storage temperature exceeds the glass transition lines. So 1, 2, 3, 4 times, 5 times the glass transition was exceeded. And that's why, of course, caking can develop then. You can see here on the right side the cake strength at a consolidation stress of 20 kilopascal, how it developed. You can see that for the low moisture content SMP, there is no caking at the end, so everything is fine. But for the higher moisture content at 4% and 4.2, we have lump formation. Here, for the 4.0% moisture content, lumps were formed or can be expected to be formed at 50 days of storage. And yeah, the highest moisture content here, the powder arrives as a massive block at the customer, and will not be very happy with this one, I think. And so from this, when you expect such a temperature or humidity profile during transportation, of course, it's necessary to adjust the initial moisture content, for example, by changing the process conditions to reduce the caking probability. So in this case, you should reduce to below 4% when you have such a temperature profile in the container. Yeah, here I want to show you how now it's possible to change the moisture content in the spray drying process. On the left-hand side here, the drying air conditions or the drying parameters are listed, for which the magnitude of the influence is known for the powder moisture content. The inlet temperature, the outlet temperature, the total solid content, and the absolute air humidity. The variations shown lead to increase or decrease in the powder moisture content of 0.2% and a change in the glass transition temperature of 2 degrees Celsius. So, for example, the decrease in the outlet temperature by 1 degree Celsius here will increase the powder moisture by 0.2% and will decrease the glass transition by 2 degrees Celsius. And also the absolute humidity, an increase of 2.8 gram per kilogram in the inlet air of the spray dryer will increase the moisture content by 0.2. This can be the result of, for example, a rainy day during production. So this seems to be a very small change in the powder moisture content, but however, when you look at the storage stability, you can see that this has a dramatic effect. You can see that the storage stability decreases by 70% when you increase the powder moisture, or yeah, this changes then the glass transition, and yeah, you exceed then at specific storage temperature, you exceed the glass transition, so you have very low storage stability then, and it can be possible that yeah, the powder is caked then after some storage time. Yeah, apart from skim milk powder, we also investigated some milk powders with different fat contents. From experience, we know that that milk powders with fat also exhibit caking problems below the glass transition. Although when the amorphous lactose is in the stable state or in the glassy state, so that's why the milk fat can contribute to this caking behavior. And in here we show I show you the unconfined yield strength at the function of the temperature for the 3 milk powders we tested. Here you can see the initial unconfined yield strength at the beginning of the tests, and then with heating of these milk powders, the roller dried whole milk powder and the cream powder increased a little bit its strength, and the whole milk powder did not do this. And with decreasing temperature then during cooling, we can see that below 20 degrees Celsius, then the powder strength started to increase for the whole milk powder, the roller dried, and for the cream powder also. Yeah, this was probably due to the crystallization of the liquefied milk fat, which is mostly at the outer part of the particle. And yeah, the lower the temperature, the more fat will crystallize and solidify the fat, the liquid fat bridges, which formed at higher temperatures. And we extracted the surface fat from the milk powders with petroleum spirit for 15 minutes to estimate the surface fat content. And here you can see the unconfined yield strength as a function of the surface fat content. And at 10 degrees Celsius, we can see that the powder strength increases with increasing surface fat content and approximately at fat contents higher than 6% at the surface, there is caking probability is high. So this is what we can keep in mind. And however, at higher temperatures here at 40 degrees Celsius, there's only a low increase in the unconfined yield strengths of the powders. So let me summarize the presentation. Amorphous caking of skim milk powder we have investigated. Here we said that we can define a critical cake strength at 20 kilopascal. At this strength, a significant amount of powder was retained by a sieve, so there is mechanical resistance at this cake strength. We saw that the cake strength increased nearly linearly with time above glass transition, and the caking time at glass transition was in the range of 130 to 600 hours, and the caking time decreases sharply with increasing temperature difference and storage pressure. Yeah, for the fat caking of milk powders, the heating to 40 degrees Celsius and the cooling affects the cake strength below 20 degrees Celsius. So the cake strength increased below this temperature due to fat crystallization. And caking problems can be expected when the surface fat content is higher than 6%. The prospect, what we want to do in the future, we want to investigate the influence of particle size on caking, because now we have only investigated one particle size, and also maybe the amorphous content is quite interesting when this changes, how the caking can change. Of course, the caking behavior under temperature humidity cycles are also interesting, whether the sinter bridge hardness will change maybe after cooling and heating again above the glass transition will be a question. And of course, the caking behavior of herbal powders, because the trend is more and more consumers eat vegetable products, so there will be the trend to plant-based food powders. So it's interesting to characterize these powders with flowability and also caking. So then, thank you very much for your attention. And here are my contact data. If you would like to contact me, you can do this via email or phone me for powder analyzers also, or for further information. And here I have also some literature you can read maybe to get also a deeper understanding of caking of dairy powders. So then, yes, thank you very much.
Thank you, Frank,
for listening.
Thank you, Frank. Matt is asking, what was the size of the sieve you were using?
This was 180 micron. 180 micron. The sieve size, yeah.
Okay. And Young is asking, why did you choose to store your powders between 40 and 50 degrees Celsius and not at room temperature for the share testing?
Yeah, this was because the powder comes from the spray dryer with this 4% moisture in the normally. So in the range of 3.6 to 4% moisture, the spray dried powders leave the tower, and then they are stored. And because we had this information from the local dairies that they have these problems with the high temperatures in the container, so that's why we try to simulate as much as possible to these real values, these high temperatures. We want to know the caking behavior during this transportation when the bags are stored in this high temperature environment. That's why we concentrated in these last studies on these high temperatures, but we also did studies where we consolidate and measure the cake strengths at lower temperatures and higher relative humidities.
Okay. Matt is going back to the sieve. Was the sieve size based on the D50 of the particle size before testing, or?
It was based on the D90. So it was bigger than the D90, so that when the powder is still not caked, then all the powder would go through the sieve. That's why we choose this size.
Okay. Thank you, Frank. So